So, PV diagrams. So, here we plot volume this side along this is the direction of increase of volume. Here we have plotted pressure. So, along the y-axis the pressure increases. So, now if volume is kept constant, then the process is like this, A to B. So, here in the entire process the pressure is constant and the volume is changing. So, this process is named as isobaric process. Isobaric process. Now, if volume has to be kept constant, then suppose C to D I have moved. So, the volume you see it is constant. So, this will be isochoric process. So, this process CD is isochoric process. Now, let us come to isothermal process. So, isochoric process. So, why this diagram is important? Because here we can show graphically the different processes through which our perfect gas, the ideal gas goes on. So, isochoric process means volume is kept constant. So, isobaric process means pressure is kept constant. Next, isothermal process. So, here temperature is kept constant. So, in an isotherm, this is volume and this is pressure. So, let us write the equation. PV is equal to number of moles R into T. So, if this is constant, we will get P is proportional to 1 by V, which is our Boyle's law. So, at constant temperature, pressure is proportional to 1 by V. So, this represents a rectangular hyperbola. So, this represents a rectangular hyperbola. The asymptotes is pressure axis and volume axis. So, we call this curve as isotherm. So, all the points, suppose this is P and this is V. These are the coordinates. We call these thermodynamic coordinates. So, all the points will have the same temperature. So, we call this an isotherm. So, what is an isotherm? Definition: isotherm. So, let us talk some technical terms. Isotherm, it is the locus of points, which points? Thermodynamic coordinates which has same temperature. So, we have this isotherm. So, if temperature is constant, this is called an isotherm. So, all the points here will have the same temperature. Now, let us see that this is again the same indicator diagram. Here volume axis and here pressure axis. So, we have an isotherm of temperature T1. So, now you see this is rectangular hyperbola. That means you see if I draw a 45-degree line, it intersects at this point. So, you see this is PV is equal to nRT, that term is constant. Let us call this C. So P is equal to C by V. So at this point, suppose this is 45 degree, you see here the magnitude of this quantity and this quantity is same. So pressure and volume is same. That means if P is, suppose I say it is V, so here this and this quantity will be same, and that will be equal to root C. So here pressure will be equal to root C. So root C. So this P will be equal to root C and this volume will be equal to root C. So this will be this square plus this square. So this length will be equal to V square, that is C square 2C square. So 2C square root means it will be root 2C something. So this will be root 2C. Now C is here proportional to T. That means this length is proportional to T. So when this length is proportional to T, so let us be clean here. So what we got, this quantity, suppose O to AI, right? So you see this quantity OA. So if I divide these angles, then OA is proportional to the temperature. So this is the rectangular hyperbola and T1 is the temperature, so it's OA. Now I have another rectangular hyperbola for temperature T2. So you see again you extended this point, that means this is OB. So OB is larger than OA, and OB represents something T2. So that means, so this is T3, where T3 is greater than T2 is greater than T1. So if temperature rises, then the rectangular hyperbolas will be away from the origin. So very important point, when the temperature is increased, then the isotherms go away from the origins. So now let us see, we have a PV diagram and we have an isotherm like this. So here is the place where our gas is. The thermodynamic state of our gaseous system is here, and it is gone through different processes. So there are different ways in which it can be carried. So this is process 1. We can go along process 2 from here, O2, then 3, then O2 4 we can go, O2 5 we can go, O2 6, O2 7, O2 8. So in which of the processes the temperature is increasing? So the question is, in which of the processes the temperature increases? So you see here, this has a temperature T. So all the lines on this will have the temperature T. So all the points which are along this will have a lower temperature. So the processes which are circled, these processes, in these processes, the temperature will increase. So 1, 2 and 3 are the processes where temperature increases. And in rest of the case, that is 4, 5, 6, 7, 8. Everywhere the temperature is decreasing because we are going, you see, just another isotherm of lower temperature, another isotherm of lower temperature. So the temperature is here decreasing. So we can see all these things. We can evaluate how temperature changes just by seeing this diagram. Let us take one more example. So here in this example, this is the PV diagram and this is a straight path. So here the pressure is P0 to P0 and here volume is V0 and 2 V0. So we carry on a process from A to B. So during this process, what is the maximum temperature attained? This is our question. During the process from A to B, what is the maximum temperature attained and where? It is given here temperature is T0. So we have to find where and how much is the maximum temperature attained by the gas, by the system. So now let us see this graphically. This is PV graph and the slope of this is 45 degree because this is here, you can see the slope is 45. So this is 2 P0, 2 V0 suppose. So we have here slope as P0 by V0, we can say. Now here temperature is given as T0, which is actually the pressure, that is PV by NR. So PV value at this place and this place is same. Here it is 2 P0 V0 and here 2 P0 V0. So if PV is same, by NR is temperature. So these 2 points have same temperature. So we can say that they lie on an isotherm. So they lie on an isotherm whose temperature is given by T0. Now let us imagine another isotherm whose temperature is slightly more than T0. That means this is from A to B. So when I go here, the temperature is increasing. So next higher isotherm means which has more temperature. So here temperature increases. So again, and here also you see this temperature is more than this and this is more than this. So as we are going, temperature is increasing. So you see again here this temperature is more than this and this is more than this. So a stage will come when there we will get an isotherm which will just touch this line. Touch this line. So when this isotherm will touch this line, that means this is the isotherm whose temperature is more than all these isotherms. So you see, as you go on towards the mid, the temperature increases, becomes maximum. This is the T maximum, and then it decreases and finally again it comes to T0. So we have T0 is equal to PV. Here P0 is 2 P0 V0. So 2 P0 V0 by NR. Now at this place we have, this is V0 and 2 V0. So it is 3 by 2 V0 and the pressure will be 3 by 2 P0. So Tmax we see is equal to PV by NR. That PV is how much? 3 by 2 P0 into 3 by 2 V0 by NR. That is 9 by 4 P0 V0 by NR. So you see this is P naught V naught by NR is equal to T naught by 2, 9 by 8 T naught. So P naught V naught by NR is T naught by 2. So we have the maximum temperature as 9 by 8 T naught, and this happens at the center of this place. So this is the place where we have maximum temperature. So you see, as you go on, initially the temperature rises to T max and then finally decreases back to T naught. So here T naught, here T naught, and at this place we have the maximum temperature.